Welcome back to AS Chemistry. In this Theme 1.4, we'll explore the different states of matter, gases, liquids, and solids. We'll see how the kinetic theory explains gas behavior, why real gases sometimes deviate, and how intermolecular forces affect properties such as boiling points, solubility, and conductivity. We'll also compare different solid structures like diamond, graphite, silicon dioxide, ice, and modern carbon allotropes such as fullerenes and nanotubes. And we'll practice some exam-style calculations along the way. Kinetic theory of gases. The kinetic theory describes how gas molecules behave. In an ideal gas, particles move rapidly and randomly. The distance between particles is so large that their volume is considered negligible. There are no forces of attraction or repulsion between the molecules. Collisions are perfectly elastic, so no kinetic energy is lost. And finally, temperature is directly related to the average kinetic energy of the particles. Gases behave most ideally at high temperature and low pressure, when the particles are far apart. But in reality, gases are not perfectly ideal. At low temperature and high pressure, molecules come closer together. They do attract each other with van der Waals forces, and their actual volume cannot be ignored. This explains why real gases deviate from the ideal gas law. Exam tip. Examiners often ask you to state why real gases deviate. Always mention intermolecular forces and molecular volume. Ideal gas equation. The behavior of gases can be described by the equation PV equals nRT. Pressure multiplied by volume equals the number of moles times the gas constant times temperature. Pressure is measured in pascals, volume in cubic meters, temperature in Kelvin. You can also use the combined gas law, P1 V1 over T1 equals P2 V2 over T2. Another important idea is partial pressure. The partial pressure of a gas is equal to its mole fraction multiplied by the total pressure. Worked example 1, gas volume calculation. Question. Calculate the volume occupied by 2 moles of oxygen gas at 298 Kelvin and 100 kilopascals. Step 1. Write down the gas equation. PV equals nRT. Step 2. Substitute the values. Pressure equals 100,000 pascals. Moles equals 2. R equals 8.31. Temperature equals 298. Step 3. Rearrange for volume. V equals nRT over P. Step 4. Put in the numbers. V equals 2 times 8.31 times 298 divided by 100,000. Final answer. The volume is about 0.049 cubic meters or 49 decimeters cubed. Exam tip. Always check units, pressure in pascals, volume in cubic meters, temperature in Kelvin. Most errors come from unit conversion, liquid state, and vapor pressure. In liquids, particles are close together, but they can slide past one another. They move with random motion, and their intermolecular forces are weaker than in solids. The enthalpy of fusion is the energy needed to change 1 mole of a solid into a liquid at its melting point. The enthalpy of vaporization is the energy needed to change 1 mole of liquid into gas at its boiling point. When a liquid is heated, particles move faster. Some particles with the highest energy escape first, which is evaporation. At the boiling point, enough particles escape to turn the liquid into gas. In a closed container, evaporation leads to equilibrium. Particles leave the liquid, but some return to it until the rates balance. This creates vapor pressure. Exam tip: vapor pressure always increases with temperature. Crystallization and water of crystallization. Some salts are anhydrous. They contain no water. Others are hydrated. They have water molecules built into their crystal lattice. These molecules are called water of crystallization. For example, blue copper sulfate crystals are CuSO4.5H2O. Solubility and conductivity. Solids usually become more soluble as temperature increases, because more energy is available to overcome forces between particles. But gases become less soluble as temperature rises, since they tend to escape from solution. Metals are good conductors of both heat and electricity because of delocalized electrons. Gases are poor conductors, while liquids fall in between. Solid structures. Now let's look at solids. Ionic lattices consist of positive and negative ions held together by strong electrostatic attraction. They are hard, brittle, and have high melting points. Metallic lattices consist of positive ions in a sea of delocalized electrons. They conduct heat and electricity and are malleable. Simple molecular solids, like iodine, are held together by weak van der Waals forces, so they have low melting and boiling points. Macromolecular solids, such as diamond, graphite, and silicon dioxide, have strong covalent bonds extending through the structure. Diamond has a tetrahedral structure with each carbon bonded to 4 others. It is extremely hard, has a high melting point, and does not conduct electricity. Graphite is very different. Each carbon forms 3 bonds, leaving 1 delocalized electron. These electrons move freely between the layers, allowing graphite to conduct electricity. The layers are held together by weak van der Waals forces, so they can slide, making graphite soft and slippery. Silicon dioxide, or quartz, has a structure similar to diamond. Each silicon atom bonds to 4 oxygen atoms, and each oxygen to 2 silicons. This creates a strong giant lattice with high melting point. Ice is a hydrogen-bonded lattice. Each water molecule forms 2 hydrogen bonds, creating an open hexagonal structure. Because of the spaces between molecules, ice is less dense than liquid water. Worked example 2, ice density. Question: explain why ice is less dense than liquid water. Answer: in ice, hydrogen bonds hold water molecules in an open hexagonal arrangement with large gaps. In liquid water, many hydrogen bonds break, allowing molecules to pack closer together. Therefore, ice has fewer molecules per unit volume than liquid water, making it less dense. Exam tip: always mention open structure due to hydrogen bonding when explaining ice density. Molecular solids, iodine and carbon nanoforms. Iodine forms a simple molecular lattice. It is a dark gray solid that sublimes to a purple vapor. The molecules are held together by weak van der Waals forces. Carbon also forms modern allotropes. Fullerenes, such as C60, have carbon atoms arranged in pentagons and hexagons, forming hollow spheres. They are strong, conduct electricity, and have unusual chemical properties. Nanotubes are cylinders made of hexagonal carbon rings. They are very strong, conduct heat and electricity, and are used in nanotechnology and material science. Closing recap. In this Theme 1.4, we studied the three states of matter through kinetic theory and real gas behavior. We examined liquids and vapor pressure, solubility, conductivity, and the structures of solids such as diamond, graphite, silicon dioxide, ice, iodine, and nanocarbons. We also solved exam-style problems using PV equals nRT and explained the unusual density of ice. These ideas link microscopic particle behavior to macroscopic properties. Master them, and you'll be able to confidently tackle states of matter questions in your AS exams.